Hello everyone. So in today's video, we are going to go over this paper, Knowledge Neuron in Pre-trained Transformers. This is by Dai et al. From the authors are from Peking University and Microsoft Research. So overall, this is a fairly recent paper. You can see it's dated 10th of March 2022, and I believe I'm not sure where this was published, but it was at a top tier conference. So what I've already gone through this paper once and highlighted some stuff which might be more relevant or something which I can provide more emphasis on. All right. So for the abstract, large-scale pre-trained transfer language models are surprisingly good at recalling factual knowledge presented in the training corpus. So if you ask GPT-2 what the capital of France is and ask it to complete the sentence, it would highly likely say the answer to be Paris. So in this paper, we present preliminary studies on how factual knowledge is stored in transformers by introducing the concept of knowledge neurons. So this is the terminology which they're going to use. And specifically, they only examine the fill in the blank closed tasks for BERT. So there are papers who investigate autoregressive tasks. There are papers which also examine, I guess, classification tasks. So there's this paper on skill neurons, which does this for classification tasks, and then there's I believe a paper by Baulab called Rome, which does it for autoregressive factual knowledge checks. So given a relational fact, we propose a knowledge attribution method to identify the neurons that exhibit that fact or express that fact, and they find that the activation of such knowledge neurons is positively correlated to the expression of the corresponding fact. So in our case study, we attempt to leverage knowledge neurons to edit, so update and erase specific factual knowledge without fine tuning. And this also sheds light on how knowledge is stored within pre-trained transformers, and the code is out there as well, and the code is pretty good. I ran some experiments myself for some other work, but it just ran without any hiccups. Also it's there on Colab, so you there's very little you can do wrong unless your code itself did not work. Alright, so large-scale pre-trained transformers are usually learned with a language modeling objective on large-scale corpora such as Wikipedia, where exist oceans of factual knowledge. Pre-trained language models naturally play as a free text knowledge base by predicting texts. So Petroni et al. And Jiang et al. Probe factual knowledge stored in pre-trained language models by filling the blank closed queries. So they ask it to fill and then compare against the ground truth. The evaluation shows that pre-trained transformers have a strong ability to recall factual knowledge without any fine-tuning. Roberts et al. Use closed book Q&A to show that the larger a model, the more knowledge it can store. This is also a bit more intuitive because the larger the model, the more parameters it has to store information. However, most previous work focuses on evaluating the overall accuracy of the form knowledge prediction. In this paper, they attempt to look deeper into the pre-trained transformers and investigate how factual knowledge is stored inside them. So as shown in figure 1, they propose a knowledge attribution method to identify the neurons that express a relational fact where such neurons are named knowledge neurons. So a relational fact could be things like Dublin is the capital of Ireland. So if you look at this here, I took the example from here only. So you have this entire thing which is your encoder block, right? So you have this self-attention layer which they're not concerned about. They're only looking into the feed-forward layer because previous works have shown that feed-forward layers are what store fact or what act as key value stores. So they see that these two neurons are more correlated with the output. So they can attribute the knowledge about this relation of this fact into these neurons. Specifically, they view feed-forward layer, that is the two-layer perceptron modules in transformer as key value memories, which was shown by Jiva et al. For example, in figure 1, the hidden state is fed into the first linear layer and activates knowledge neurons. Then the second linear layer integrates the corresponding memory vectors. So how does this integrate it? You first have some uh, matrix multiplication result, which then gets multiplied by a second matrix, which does this transformation. So this matrix acts as the values matrix, and the output here acts as a coefficient to scale those value matrix columns or rows. The key value memory nature inspires us to propose the knowledge attribution method, which identifies knowledge neurons in feed-forward networks by computing the contribution of each neuron to the knowledge prediction. So extensive analysis shows that the activation of the identified knowledge neurons is positively correlated, which is good, to the knowledge expression, which shows the effectiveness of the proposed knowledge attribution method. First, suppressing and amplifying knowledge neurons notably affects the expression of the corresponding knowledge, which means that they have some, at least some notion of the knowledge. Second, we find that knowledge neurons of fact tend to be activated more by corresponding knowledge expressing prompts. So a prompt like I liked and then an empty blank would not likely activate a neuron which stores facts about, say, the capitals. Third, given the knowledge neurons of a fact, the top activating prompts retrieved from the open domain text usually express the corresponding fact, while the bottom activating prompts do not express the correct relation. So we'll see this later in the paper, but just for an example, for instance, if I say Dublin is the capital of Ireland, this is expressing the fact. But if I just say Dublin is a city in Ireland, this is not expressing the fact that there is a capital relation. It's expressing another fact that Dublin is in Ireland, but not the fact which we were looking for, the capital relation. So the authors see in the later examples that if the word capital or such explicit factual relations are not mentioned, then the prompts are, even though they have the keywords Ireland and Dublin, they are not going to activate the knowledge neurons. So in our case studies, we try to leverage knowledge neurons to explicitly edit factual knowledge in pre-trained transformers without any fine-tuning. So there are two preliminary studies, updating facts and erasing relations. After identifying the knowledge neurons, we can perform a knowledge surgery by directly modifying the parameters in the feed-forward networks. So their contributions are, they introduce knowledge neurons for fill-in-the-blank closed tasks. They conduct qualitative and quantitative analysis, and they present preliminary studies of leveraging this to edit the transformer memory. All right. So this is the transformer, and this is just something I hope you are all familiar with. A transformer has L identical blocks of encoders. Each transformer block mainly contains two modules, a self-attention module and a feed-forward network. And let's say you have an input matrix, which is n cross d. Then first you have attention calculated. So you project the input into the query key and value vectors. Then you use those to uh, create the self-attention map, and then you pass the outputs, which is the hidden state, into the first perceptron multi-layer perceptron layer, which does a matrix multiplication. You add activation, and then you again multiply it with the second fan out matrix. So these are just all of these matrices are parameter matrices. Self attention computes a single attention head H, and then the hidden state is given by projecting the concatenation of all heads. So if I hope you're familiar with multi-headed attention, you compute self-attention with a bunch of different key query value, and then you just concatenate them column wise and then project them again into the hidden dimension. And here they're using GALU activation, but I'm fairly sure the original transformer paper used ReLU activation. Also, there is a scaling term as well. So in this equation, you divide it by under root dk, which is the dimensionality of the key vector, but they've removed that. Also, they've not handled the bias terms. So if you compare equation 2 and equation 3 for uh, so these two equations right here, you can see that the formula for the feed forward network is quite similar to that of the self attention, apart from the fact that you have GALU in one and softmax in the other. So similar to the key query value mechanism in self attention, it is reasonable to regard the input of feed forward network as a query and the two linear layers as keys and values. So your uh, matrices W1 and W2 are going to act as key value pairs, and they're going to extract some knowledge. So this is just by the observation that these two equations are structurally very similar, and this is also observed by other works. So let's now see how they identify knowledge neurons. So similar to Jiva et al., they view feed-forward network as key value memories and hypothesize that they have some factual knowledge which are expressed by knowledge neurons. So now they want to have a strategy which helps them identify these knowledge neurons. And to do that, they, of course, they are only working with the fill in the blank close task, and take on they take relational facts because they only have one correct answer, and the relational facts are of the form HRT. H is the head of the entity, T is the tail entity, and R is the relation between them. So, given a fact, pre-trained models answer the closed query X and express the fact but leaves the tail entity as blank. So, you say you have I'll Dublin is the capital of. So Dublin is the head entity, capital is the relation, and your tail entity would be Ireland. Or the reverse case, Ireland capital Dublin. So the capital of Ireland is Dublin. And these are known as knowledge expressing prompts. So I hope it's clear how what data they're using. So Petroni et al. Described that a model knows a fact if it can predict the correct answer. So in this paper, rather than just examining the model outputs, they also identify the specific knowledge neurons that express the factual knowledge. So for knowledge attribution, inspired by Howe et al., we propose a knowledge attribution method based on integrated gradients. So this is a pretty famous method to perform model explainability. So our method can evaluate the contribution of each neuron to the knowledge prediction. So in this paper, they examine feed-forward nets intermediate neurons for the mass tokens where the answer is predicted. So they are going to use that to see attribute integrated method based attribution method to find knowledge neurons. So how do they do this? It's not very difficult, but it might take a bit to wrap your head around. Uh, so you have your input prompt X, so this is pretty clear. And first, define the model output, which would be the probability of the correct answer predicted by the model. So P of X is just the probability of given input prompt X, and Y star denotes the correct answer. So this probability is the probability of getting Y star given X, which is your input prompt, and then WIL is the ith neuron in the Lth feed-forward network layer. So if this value is equal to some assigned value, so you are basically assigning some value to that. Okay, I think I should make it a bit more clear. So this value is the value for the uh, ith neuron in the Lth feed-forward network layer, and wi cap l, so this value is the value which we manually assign to it. So we are going to manually assign values to neurons and then see the effect they cause. So how does this help and all, we'll see that, but the idea should be clear, I guess. If you have a neuron, traditionally it gets an input, gives an output, but now in despite in spite of whatever input we give it, the output will always be the same now, and this would be a fixed value. So in order to calculate the attribution score of a neuron, which is atter of WIL, they change WI from 0 to its original value. So what's the original value? The value which you record when you pass in the input prompt X, and the value which that neuron outputs. So you change it from, you just scale WI from 0 to the original value, and then uh, uh, integrate the gradients. So this is where the integrated gradients parts comes in. So if we just look at the equation, it might be a bit intimidating, but let's just break this down. So you have del of px over del of wil times alpha WIL. So now let's just think about what all is happening. So what is this value? I'll just use some other pen. This innermost value is the original value, OG. Then your alpha is the scaling term. So why do we need this scalar? Because you see your integration is with respect to alpha, and alpha varies from 0 to 1. And this achieves the result we want. This will scale WIL from 0 to its original value, because when it's 0, this is 0, when it's 1, it's the original value, and P of x just gives you the probability. And finally, you want to integrate the gradient. So you take the derivative with respect to the layer and lth layers ith neuron. And at every instance, you multiply it with the original value. This is just how integrated gradient works, and they define it. So when this value is low, this value would be scaled down. When this value is high, this value would be scaled up. So this gives you the attribution score of WIL. So again, they explain it. This calculates a gradient of the model output with respect to WIL. Intuitively, alpha changes from 0 to 1. By integrating the gradient, this accumulates the output probability change caused by the change of Wi. So if this change is high, then it means it's very dependent on that. So if the neuron has a great influence on the expression of a fact, the gradient will be salient, which in turn has large integration values. Therefore, the attribution score can measure the contribution of the neuron to the factual expression. So I hope this makes sense now. And this is not, I guess, if you still don't get it, maybe you can just try rewinding the video a bit, or just try reading it yourself and breaking down the equation. I guarantee it's not tough. And finally, since we all know integration, you can't just do back propagation over integration. You need to break it down somehow. They break it down into Riemann approximation. So this is like, I guess, undergrad maths, and they use 20 steps for that. So this is just approximating for doing this for through your model, because you can't really back prop through integration. And finally, with this algorithm, you can identify a coarse set of knowledge neurons whose attribution scores are greater than a threshold t, and they define that threshold t as a hyperparameter. So now you need to refine those knowledge neurons, right? Everything is not a knowledge neuron. Maybe there are some false positives and false true positives which need to be disentangled. So besides true positive neurons that express, there might be false positive neurons that express other information like syntactic or lexical information, and then thus you need to refine them. So for different prompts corresponding to the same fact, we hypothesize that the same set of true positive knowledge neurons would express the same factual knowledge, while the false positives would not activate every time if you change the prompt. So you want to keep the relation, you want to express the same fact but in different ways. So that way, the intersection of all of the different set of activations across different prompts would give you the correct set of true positive knowledge neurons in theory. So they create diverse prompts, and they refine the core set of knowledge neurons by only retaining neurons that are widely shared among these prompts. So how do they do this? They produce n diverse prompts. For each prompt, they calculate the knowledge attribution scores. For each prompt, retain the neurons with the attribution scores greater than the threshold. And considering all the core set, retain the knowledge neurons shared by more than p% prompts. So I guess this is pretty intuitive how this works and why this is working. So I won't spend a lot of time on this. This is just an algorithm, and they can use this to find their own true positive knowledge neurons. So now let's have a look at their experimental setup once. So they use BERT, 12 transformer blocks, 768 hidden size, and the hidden size of the feed-forward network's inner layer is 3072. And of course, this method can be applied to other models apart from BERT as well. So for each prompt, they set the attribution threshold T to zero point 0.2 times the maximum attribution score. So What this means is that if, say, the highest attribution score was 10, the attribution threshold is 2, and every neuron with higher activation than 2 would be a part of the set of knowledge neurons. And for each relation, they refine the threshold, like the threshold to see the neurons which occur in more than these number of prompts, which activate in more than these for more than these number of prompts, would be a knowledge neuron for that fact, and they take that as zero point 0.7. So these are arbitrary, but they must have done experiments to finalize on this, and they increase or decrease this value by 0.05 at a time till the average number of knowledge neurons lies in 2 to 5. So the zero point 0.7 value is not static. Say for zero point 0.7 you don't get any neurons, then you reduce this to 0.65, and if you get a lot of neurons, then you increase this to 0.75. And on average it costs 13.3 seconds to identify knowledge neurons for a relational fact with 9 prompts on V100. In my experience on the collab server with GPU on, obviously, it was taking around 4 minutes, if I'm not sure, if I'm not wrong. So of course there's a huge difference between using a V100 and the free collab servers. For dataset, they use Parallel, which is curated by experts and has 38 relations from the T-Rex dataset. And they have some examples. So for each relational fact, they fill in the head entity and they leave the tail as blank. In order to guarantee the diversity, they filter out relations with fewer than 4 prompt templates and finally keep 34 relations, where each relation has 8.63 different prompt templates on average. So this creates 253,000 prompts, and which uh, basically comprise of 27,000 facts. So let's have a look at this example. For instance, you have this manufacturer relation. So X is produced by Y, X is a product of Y, X and its Y and its product X. So these are all different ways to express the same thing. And you just fill in these templates. So now a baseline. So you also need to compare to other methods, right? So for the attribution scoring, is there any better way to do this attribution scoring? So they also check a baseline method. So they take the neuron activation as the attribution score. So they're not doing this fancy integration which is converted to a Riemann summation. They're just taking the activation to be its attribution. And after computing attribution scores, they follow the same pipeline to obtain the refined knowledge neurons. And so this does not accurately, I guess, consider the impact, but they're just trying to show that they are better than the baseline. And of course, for a fairer comparison, they again use TNP percentage to select the knowledge neurons. The method based on knowledge neuron activation is a reasonable baseline, of course, because it is motivated by the feed-forward neurons analogy with the self-attention system, because self-attention scores are usually used as strong attribution baselines for other works. So let's have a look at uh, the knowledge neurons identified in different layers. And I guess we'll go over this figure once this is mentioned. So figure 3 okay, it's mentioned right here, statistics. Figure 3 mentions the layer distribution of knowledge neurons identified by the attribution methods. We notice that the most fact-related neurons are distributed in the topmost layers, which is again agreeing with findings of Jiva, Tenney, and other works who, like your entire fine-tuning thing where you only fine-tune the last layers, uses this rationale, right? Because the last layers capture more richer features. So again, as you can see, towards the last layers, you have much higher attribution values. Table 2 shows statistics of knowledge neurons. So on average, they have 4.13 neurons for each relational fact using their method and 3.96 using the baseline method. The same order of magnitude guarantees the fairness of the comparison, because if you say took 1 and 5, then of course the comparison is not fair. And they also then perform some checks to see which ones are better. So for instance, if a fact pair shares the same relation, which is an intra-relation fact pair, it is shared 1.23. Okay, I just messed this up. Uh, so for their method, 1.23 knowledge neurons are shared on average across the same relation, and fact pairs with different relations share almost no knowledge neurons, which is also what you want, which is interrelation fact pair. And most identified neurons are shared by intra-relation fact pairs, which is of course what you want, because you want your hypothesis that some neurons are learning factual information, say about the capital, so they must activate for all different types of capitals. Even a substantial portion of neurons are common for interrelation fact pair. So this is all for the baseline. So going back, you can see these values are similar, but these values shows a sharp difference. So the intersection is very high in the baseline, but this is also very high in the interrelation ones, which we do not want. So this just shows that these methods are not really capturing what we want. So how knowledge neurons affect knowledge expression? Figure 4 and 5 show that. So given a relational fact, they manipulate the knowledge neurons in two ways. They suppress it by setting activation to 0 and amplify it by doubling the activation. And then for each relation, they plot the uh, average change ratio of the probability for the correct answer corresponding to the manipulation. And they show this here. So figure 4 shows that suppressing knowledge neurons identified by the method they propose leads to a consistent decrease in the correct probability. And you can see, right, this is the decrease in the probability. So that means that those neurons were really helping out. By contrast, for baseline ones, there's only a 1.47% decrease on average. And for instance, developer relation, the correct probability abnormally increases for the baseline, but that is not there in uh, the case where that is not true for the case with the method which they propose. So you can see this here. Figure 5 shows that we have similar observation for amplifying them. So when you amplify them, it increases significantly. By contrast, the baseline only increases by 1.27%. So this means that they are much better than the baseline. In summary, the knowledge neurons identified by the method tend to notably affect knowledge expression. And if the knowledge neurons for a relation are distributed more widely, they might need to manipulate the top k neurons for better control. But that is not what they focus on in this work. So as I was talking about, I guess we'll come to this table when we see this here, because I want to go according to the paper, right? So for section 4.6, knowledge neurons are activated by knowledge expressing prompts. So they create their own Bingrel dataset, which basically they take the facts in parallel, and then they crawl to find two types of text. So they find up to 10 texts containing both head and tail, and up to 10 texts containing only the head and not the tail. And then for the first type of entities, fact text, they mask the tail entities to obtain knowledge expressing prompts T1. And in order to conduct a control experiment, they also mask random words for the second one type of text, because they do not have the same the second tail entity. They were scraped on the basis of that, and this is a control group T2. And they also employ random sampling as another control group, which gives them T3. So as shown in table 4, uh, the knowledge neurons are more significantly identified for by knowledge expressing prompts as compared to control group prompts, and the difference is pretty significant, but the baseline does not recognize this. In addition, since our comparison is based on the web crawled Bingrel dataset, they validate the generalization of knowledge neurons to open domain texts that are unseen in parallel. So this is not something which the model has seen before. Also, some example prompts are given. So for in table 3, they show the top two and the bottom two activating prompts for a particular neuron. So given a fact, we first identify its knowledge neurons with our knowledge attribution method. We calculate the average activation of the knowledge prompts for each crawled prompt that contain both the head and tail entities in Bingrel. And finally, they demonstrate two prompts with the highest average activation and two prompts with the lowest activation. So the top two activating prompts express exactly the corresponding relational fact which I was talking about, but the bottom two activating facts do not express the correct relation. For instance, if you look at Ireland capital Dublin, the Dublin is a city in Ireland does not exactly reflect the capital relation, so that comes in the bottom two. So again, if we go here, we can see the top two show the capital relation, while the bottom two just show iconic destination or city and not the capital relation. Then they do some case studies. So these are for updating and erasing relations. So for the first one, they want to change the tail entity from some T to a T dash. To identify this, first identify knowledge neurons for the fact. Then we retain the knowledge neurons that are shared by less than 10% of the interrelational fact to reduce the influence on other facts with the same relation. So this basically means that they are not trying to minimize the effect which updating one fact would have on other facts. And then they simply want to update the feed forward network's value slot. So to do this, they basically convert T and T dash into their embeddings, which you can just get from anywhere, the word embeddings. And then they subtract the word embedding for the original one and add the for the other one, and they scale it by lambda 1 and lambda 2. I believe they show what lambda 1 and lambda 2 worked best. uh, Maybe it's there in the appendix. So lambda 1 and lambda 2 vary from 1 to 8. And so for the setup, we randomly choose a different entity T dash, and T dash also belongs to the same set, right? So you can't change the capital of Paris is to Bacon. You want it to be a city. And so they manipulate the top four knowledge neurons for reference purpose. They also perform the same update process on a number of random neurons to see the success rate, and you can see the difference is quite significant. And for evaluation, the change rate, so the ratio that the original prediction T is modified to another, the success rate that it becomes the top prediction, and they also measure the influence on other metrics. So they have intra-relational PPL, so they increase the perplexity, and interrelational PPL, they increase the perplexity with different relations. And both of them are not very uh, so this for this the lower the better. So the first one intra-relational is better, but interrelational increases. So there is some effect which further works can try to minimize. So as shown in table 6, the surgery of knowledge neurons achieves a non-trivial success rate. It is promising that you can only change 4 neurons to get such good results. And this is for your updation. And table 5 is for erasing, which we go over now. So for erasing relation, they explore how to leverage knowledge neurons to erase specific relations. They take 4 relations: place of birth, country of citizenship, occupation, and work location. So for methods, they first identify the neurons, and they for all the relational facts with the given relation, and they keep the 20 knowledge neurons that appear most frequently. Finally, they set the value slots in these to 0. So that means that they're trying to make sure that these are not giving any input to the model. They report the perplexity before and after. So with erasing, the perplexity increases, which you expect because you're taking away the model's ability without even telling the model. And the perplexity of other relation remains similar. They argue that knowledge neurons provide a positive way of updating the information. So you can see the perplexity is significantly higher, but the perplexity on the other relations decreases. It's not as high. So of course this would be expected because now the top tokens would change. But here they should not have changed, and these results show that they haven't. So now some related works. You have probing works, which we discussed. So these are just factual knowledge probing. Then you have attribution methods. So in order to open black box, there have been methods to see what do these score store. So the product of the gradients and feature values is a reasonable baseline, which some work showed. Besides a set of attribution methods, some works back propagate the final output to input features, but these are not very good methods. That is why integrated methods was developed by Sundara Rajan et al. So these methods lack sensitivity and implementation invariance together. So taking these axioms, the integrated gradient works uh, achieves both of these together. And for the analysis of transformer, there have been a lot of works which have pointed out that feed-forward module are significant to the model. And Jiva et al. Showed that feed-forward networks with memory act like key memory layers. And their analysis was more qualitative, but this is a bit more quantitative. So for conclusion, they find suppressing or amplifying the activation of knowledge neurons can affect the model, so they some automated methods could be maybe found out for the same, and their work is limited to fill in the blank task, but that is not all there is to the world, right? I would argue that classification and autoregressive tasks are much more frequent in literature, and there are works which do the same. Second, even though the model is applicable for okay, the interaction between knowledge neurons also remain underexplored. So that is one thing. How does one knowledge neuron learn or affect the other? Second, even though the model is method is applicable for other types of knowledge, factual, they only focus on factual knowledge, so that can also be explored. And thirdly, single word fill in the blank close queries are much simpler to implement, which they've done, but multi-word extensions can also be done. Finally, they thank the people and the organizations which supported them. So overall, this is a great paper to read. Not very mathematically heavy. The arguments are very good, and I really like this paper. So I hope you took away something from this video. And thank you guys for joining in. Hope to see you again next time as well.